Hello, dear students. Very well. Welcome to the channel and welcome to another video of this video series in which we are going to discuss about mathematical operations which are being performed on various kind of signals and different systems. Up until now, we have seen some basic signal operations. We have also like addition, multiplication, subtraction, and like integration, differentiation. We have seen such operations in signals. um, After that we have talked about different type of systems. We have also seen this systems in series connection and systems in parallel connection. We also seen the cascaded systems, and in very last lecture of this lecture series, the previous lecture, in that lecture we have discussed about the LTI systems. We have seen basics of LTI systems. After that we have also seen the impulse characteristics and convolution integral. In that we have seen how convolution can be helpful to you, how it can be helpful to your signals, and what are the properties which convolution holds. So we have already gone through that. Today I'm going to discuss about the LTI system response and the properties from impulse response. But before we begin this video, there is a catch that because if you have no idea about what is LTI system in the first place, then you would not be able to learn what I'm going to discuss in this video. So uh, you must have some idea about it. The second thing, you must have some idea about convolution, because all the properties which I'm going to discuss are basically very have so much resemblance with convolution operation of signals. So you must have some idea about convolution. But even if you don't have any idea, there's no need to worry. We have covered both of these topics in very previous video we uh, shoot of this lecture series. So if you don't have any idea, feel free to check that out, check that video out. You will be finding the link which will be flashing on this I button on the top right hand side corner of your screen right now, so you can check it out from here. Second thing which I wanted to talk about here, that as we are going to discuss about the properties, and we are going to discuss about the LTI system response and properties both. So you must have some idea about the system properties. What are the properties of systems, and what does it means? So if you have that idea, it would be easy to grasp. But even if you don't have, I will try my best to make you understand that in this video. But it will be more beneficial to understand it from a separate video which I have made earlier when I was discussing about the basics of signal and systems. So in that playlist I have mentioned, I have made a separate video on system responses and the various properties of a system. So it includes all those properties which I am going to talk about right now. So if you want to learn about it, feel free to check that video out as well. The link will be given in the description below, so you can find the link in the description of that video. And now, assuming that you have idea of both of this system, let's move forward and let's try to understand what are the LTI system responses and properties from the impulse response. Okay, so earlier we have seen the properties, system properties, and what were those properties? If you remember, we had static and dynamic property. Then we had time invariance and time variant property, shift invariance, shift variant we called it. Then we had causality, we had linearity, we have stability, there was invertibility, right? We studied all those properties back then. And now what do we want to do? Now we want to consider these properties for my LTI systems, my linear my linear time invariant systems. So what I will do, I will derive the condition in terms of the impulse response. And if I'm deriving in terms of impulse response, you must have a question that why impulse response. So why impulse response I'm considering, because what impulse response does, impulse response relates my input with my output. Okay, impulse response provides that bridge between input and output. It relates my input with my output, and because of that, what I will do, what I can do, the properties of this system I can um, easily characterize in terms of impulse response. And that is the major reason why I'm considering the impulse response here. So again, you must have an idea what impulse response is, because if you don't have any idea, I'm not going to explain everything in detail, but just know that impulse response is just a singular pulse which has area is equals to 1 for a certain time period t, and except for that time period, its area will be 0, right? So you can check out all the different type of signals as well in the first playlist which I have discussed, the basics of signals and systems. And that we have covered everything about the basic signals, and impulse response is one of the very basic and very much useful signals. So we have covered about impulse response or impulse signal in that as well. So if you want to learn more about impulse, uh, go and see the lecture series. The link of that lecture series is also provided in the description below, so you can feel free to check it out anytime you want. Now coming to the properties of LTI system, the first property is dynamicity again, which also means memoryless, or memoryless system, or a system which does not hold its memory. So before discussing what is dynamicity or what is static behavior of a system, let's let it would be easier for me to show you rather than talk about it. So let's first consider this system which we have considered last time as well. So for any system we can give the convolution by uh, this formula: y of t is equals to minus infinite to infinite x of tau h of t minus tau into d tau, right? Now from the previous lecture, the very last lecture, we have learned that this convolution is commutative property. So instead of x of t into h of t minus tau, you can also write x of t minus tau into h of tau, right? So we will do exactly that. We will write x of t minus tau in place of x of tau, and we will write h of t minus tau in place of h of tau. Sorry, we will write h of tau in place of h of t minus tau. So what is the condition for a system to be a static system? So the condition is, if the present output of my system will depend only on the present input of my system, then only my system will be considered as a static system or memoryless system. Okay, so the system is said to be static or memoryless system if the present output depends only on the present input. Okay, so in this equation, this one second equation, let's try to figure out what will happen where either is it is dependent or not. So we can clearly see the output of my system y of t is clearly dependent on x of t, right? But when when the value of tau will equal to 0, right, it will be dependent on x of t when value of tau will be 0. If value of tau will be any integer number 1 2 3 4 anything, then my y of t will be dependent on x of t minus 1 or x of t minus 2 or that particular value, right? So that is only true for x of for tau is equals to 0, right? So y of t will be dependent on x of t only when tau is equals to 0. But what does it means when your tau is equals to 0, right? This means the value of my h of tau will be evaluated only at tau is equals to 0. Now do you agree with me or not? Okay, let me specify a little bit more. What is happening here, that my present input, which means my y of t, is dependent on x of t. When I can say it is dependent on x of t, it means the original signal should not be a past signal. So whenever tau will have any value, any integer value, so 1 2 3 4 5 anything, that will make the value of x of t minus tau a past input, right? So the situation or the condition is only true for tau is equals to 0. Now when we will consider tau is equals to 0, which means uh, h of tau is not 0, right? If uh, or h of 0 is not 0. Do you agree with me or not now? Because if h of tau, we are taking tau is equals to 0, which means h of 0, if that value would have been 0, that means what would have happened? If that value would be 0, then my whole output will be 0, right? Anything multiplied with 0 is 0. But that is not the case, which means my h of tau is evaluated only for the value of tau is equals to 0, because any other value except for tau, if I try to take any other value except for tau is equals to 0, what will happen? This input will either become the past input or it will become the future input. So for h of tau, for the value of tau is equals to 0, only I can find my system static. And what does it means? It means h of tau is evaluated only at tau is equals to 0. Okay, so we represented it mathematically that h of tau is equals to 0 for tau does not equals to all the zeros. Right, now it makes sense. H of tau is equals to 0 for all the taus does not equals to 0. When the value of tau will be equal to 0, uh, h of tau will have some value, right? And now that I have already described that, do you remember, does that rings any bells, that what signal does this equation or does this description looks like? If you have seen the videos for impulse signals, this is impulse signal. This is exact description of my impulse signal, right? So based on this description, I can say that the h of tau is actually a weighted impulse which is defined only at tau is equals to 0, right? And only under this condition the system will be a memoryless system or a static system. So when I consider my h of tau is equals to uh, my weighted impulse or c into delta tau, and what I will do this time instead of h of tau in this equation, instead of tau I will mention c delta tau. So I will just substitute the value of h of tau here, and let's see what we come up with. So we are getting here y of t is equals to minus infinite to infinite. The x of t minus tau will remain as it was, and instead of h of tau we will be getting c delta tau into d tau. Okay, now as we all know c is a constant, so we will take the c out and we will represent the term again, minus infinite to infinite x of t minus tau del tau into d tau. And again, when you see this equation, it has uh, uh, it has great resemblance with the equation of convolution, right? Great resemblance with this equation, which means it is nothing but the convolution of my x of tau with del tau with c constant c, uh, with constant c as a multiplier with this convolution, convolving signals, right? So what did we learn here? That the convolution is becoming a scaling operation for my static systems or my memoryless systems, and because of that we can say that the system is memoryless or a static system only and only the value of my h will be c into delta t, right? The system will be system will be a stable system, oh sorry, not stable, system will be a static system or memoryless system only when my h of t will be c delta t. Instead of tau we just simply wrote t, right? It's basically this same equation, but instead of tau we just simply wrote t. So that was the condition for your dynamicity. Basically we were checking either my system was a static system or not. So this is the condition. If my system satisfies this condition, which means my system is a static system or a memoryless system. If it doesn't satisfy that system, which that would mean that system is a dynamic system, and it is a system which holds memory. Okay, now let's come to the second property, the causality property. So again let's do the same thing. Let's take the same signal and represent it with the same convolution formula. So y of t will be is equals to minus infinite to infinite h of tau x of t minus tau into d tau. Now if you remember, when did we called a system a causal system? How do you define if your system is a causal system or a non-causal system? What was the condition? So if you know the condition that the system will be said or will be called a causal system if its output depends on present and past inputs only, right? It should not involve any future inputs. If your system involves any future inputs, or if your output of your system will depend on any future input, that means your system is a non-causal system. So let's try to do a little bit analysis here. So based on this formula, what can we say? So for once focus on this value, x of t minus tau. Now the x of t is the present input, right? X of t is my present input. But what will happen for in the case of x of t minus tau? So let's think about it. uh, X of t minus tau, let's try to consider, let's try to take any values of tau greater than 0. Okay, 1 2 3 4 5, you can consider any. So for all of the values of tau greater than 0, x of t minus tau will be are your past inputs for tau greater than 0. How? So let's consider few cases. Let's take tau is equals to 1. So when you take tau is equals to 1, what will be the equation, or what will be the formula? X of t minus 1, right? As you are considering t minus 1, which means it is a past input to your t, because what is the present input? X of t, right? If I'm considering x of t minus 1, it means this that is a past input. Then consider 2, x of t minus 2, again past input. 3, x of t minus 3, again past input. So no matter how far you go for tau greater than 0, x of t minus tau will always be past inputs for all the values of tau that is greater than 0. Same way as when we consider for the values of for negative values of tau, what will happen? Let's try to consider the tau is equals to -1. So x of t minus tau, what will be the value of x of t minus tau? We already had a negative sign ahead of tau operation, so we will have uh, negative into negative will become positive, so we will have x of t plus 1. So what is x of t plus 1? Your present input is x of t, right? If you are going x of t plus 1, that will become your future input, right? So for all the values of t less than 0, for all the values of tau less than zeros, x of t minus tau are future input only, right? So what will happen? What do you need in this convolution operation? So the result of the convolution must be 0 for all the future inputs, which means for all these values tau less than 0, right? And if the system is causal, then what will happen? H of tau or x of t minus tau, like when my system is causal, what happens in this formula, right? System is causal means your output is only dependent on present input only, right? Your output is completely dependent on present input only. So what will happen? Either h of tau or x of t minus tau, either one of them must have to be 0 for t less than 0, right? For your system to be a causal system. Are you understanding? What do we have to do? For all the systems for which the value of tau is less than 0, your x of t minus tau will become future input. So we cannot consider that we cannot consider the values of tau less than 0, right? So either h of tau or x of t minus tau, either one of them must be 0 for tau less than 0, right? When tau will be less than 0, which means uh, when I put value of tau is equals to -1 here, so it will be h of -1 into x of t minus 1, right? So and your output will be still y of t, right? So it will not be causal, right? So in that regard, what needed to be happen, that either h of tau or x of t minus tau must be 0 for the value of tau less than 0 if you want to make your system causal, right? Consider this x of t minus tau is equals to 0 and the value of your tau is -1. Now see, y of t is equals to h of -1. There is no t here, right? So your system is causal. Your output is not dependent on future input, right? So and also I've just said let's consider x of t minus tau is equals to 0, but it cannot be 0. Why? Because it was representing future inputs. So what does it means? It means my h of tau must be 0 for for tau less than 0 if I want my system to be a causal system, right? So we just derived the condition for my system to be a causal system. What is the condition? So the value of h of t must be equal to 0 for all t less than 0. For all the values of t which are less than 0, the value of my h of t should be 0. Now what do you indicate, what do you learn from this condition? That the condition is showing that the impulse response of a causal system is also causal, right? And now when we are having this condition, h of tau is equals to 0 for all the values of tau less than 0, we can also modify the integration limits, right, in my original equation, my convolution equation, right? So uh, come here and see that for t less than 0 we are having. So what will become here, y of t is equals to minus infinite to infinite h of tau x of t minus tau into d tau. But for all the values for t less than 0, if we are considering, so what we will do this time, right, for we are considering tau less than 0, right? So what will happen, it will be the negative points or any negative numbers will not be considered, right? Because we want our system to be causal, and almost every system is causal in practical situations. So what will be the condition, it will be 0 to infinite h of tau x of t minus tau into d tau. Okay, for all the negative values you are not considering, so it will be 0 to infinite h of tau x of t minus tau into d tau. And same ways you can write, because we just talked about the commutative property of convolution integral, so we can also write y of t is equals to 0 to infinite x of tau into h of t minus tau into d tau. So that was your causality property. Now the third property is the stability property. Again, let's try to learn it from the equation, and again the equation for the convolution will remain same, which you can see in the first equation, convolution equation it is presenting. Now let's try to apply modulus. Let's try to see what will happen when we take modulus of the whole equation. So we have applied modulus on left hand side and right hand side, and after doing that we can find the magnitude of my output, right? But as we have applied modulus, and as we are going to talk about stability here, right? So what we can do, we can represent the right hand side of the equation as this equation as well. We can also write less or equal to, right? We are not changing anything in the equation, huh? We are keeping y of t as it is, we are keeping the right hand side as it is, minus infinite to infinite h of tau x of t minus tau into d tau. So we are keeping everything as it is, but what did we do, we just took the bracket here, and we just put the bracket over my original values h of tau into x of t minus tau, and we separated the integral limits separate. So we can write it this way as well. And after this, what did we do, we just put this separate modulus over h of tau and over x of t minus tau. Now before we move further, I would like you to recall what was the condition for a system to be a stable system. So if you don't remember, let me tell you, the system is said to be a stable system when if it produces the bounded output for every bounded input, right? So we all know the output in our system is y of t, right? So when my output will be considered bounded, so if you remember, the condition was y of t less or equals to my less than infinity, which means your output uh, should be a finite value. Now let's try to use this condition, and let's try to use this condition in this formula here. So what will happen, uh, we will take minus infinite to infinite h of tau x of t minus tau into d tau, and what did we do, we just took this equation and we just substituted value of yt, this value or this value, you can take either of these value, into here. So we just substituted it, this is the value of my y less or equal to my less than infinity. Okay, now um one one important thing one important thing, that a system is stable if bounded output as given here is produced for bounded input only. So what does it means? Your input should also be bounded, which means my x of t should also be bounded. So again, x of t lesser equal to mx less than infinite, and x of t minus tau lesser equal to mx less than infinite. We took that. And what will happen with x of t minus tau here? See, the value of x of t minus tau will be considered bounded if the maximum value will be mx. And what we will do, we will just simply put the value of x of t minus tau is equals to mx in which equation? In this equation. So we just took minus infinite to infinite h of t, h of tau, sorry, multiplied with what did value we take? We took mx. Okay, so mx into dt d tau lesser equal to my less than infinite. Now the mx will be a constant value, so we took it out of the integral, so we will be left with mx minus infinite to infinite h of tau into d tau less than infinite. And this is pretty much the condition for the system to be a stable system. So what is the condition again? So the system will be called a stable system only uh, when the output system uh, will the output will be bounded for bounded inputs, right? So the system will produce bounded output for bounded input. And what do we call that system? That stability of the system, we call it BIBO stability, bounded input bounded output stability, right? So again, this is the condition for an LTI system to be a stable system: minus infinite to infinite h of ht uh, into h tau into d tau or ht into dt less than infinite, right? And what does this condition shows? This condition shows that the bounded input and bounded output systems has absolute summable impulse response, right? We can also see it like that, like, because uh, basically what you are doing by taking integration, you are just taking addition of the system. And if it is non-zero, it is non-infinite, which means it is a finite value. That means it is a summable impulse response, it's summable value, right? Basically your h of t, it is nothing but impulse response, or it will be very much close to that, right? So that was your stability property. Now let's move forward to the step response property. So let's try to determine the step response of a system, LTI system, in terms of, again, impulse response, because we are considering impulse response here everywhere. So again, let's take the convolution equation. Y of t is equal to minus infinite to infinite h of tau x of t minus tau into d tau. And this time what we will do, we will consider my x of t is equals to a unit step signal. So again, what was the value of unit step signal? It was 1 for every value of t which is greater than 0, greater than or equal to 0, right? So if you don't remember the unit step signal, you can check out the video which I told you about, uh, the video which discusses the different type of important signals in this signal system journey of yours. So what we will do, we will take a unit step impulse, unit step signal as x of t. And as we all know, the value of unit step signal is always 1 for all the values of t greater than or equal to 0. Again, for x of t minus tau, what we will do, we will again consider a unit step signal here And for that, what will happen, u of t minus tau will be always equals to 0 again, always equals to 1 again, for all the values of t greater or equal to tau, right? Because think about it, what will happen, the value if the value of tau is equals to 3 and value of t is equals to 2, you will have uh, 2 minus 3 is equals to minus 1, x of minus 1 you will be having. And you will have u of minus 1, right? So it will be 1, it will still be 1, but it will be on the negative side, it will go to 0 to minus infinite, right? So for all the values of t which are greater than the value of tau, we will have x of t minus tau is equals to u of t minus tau, or the value simply a unit value or a value 1, right? So can't we write this equation in a different way as well, right? We are not changing this thing, we are keeping the formula as it is, but instead of t t greater than or equal to tau, we can also write tau less or equal to t, right? Either ways it's same thing, the tau is still smaller than the value of t, right? And what we will do this time, we will put this value x of t minus tau from this equation into this equation, and we will see what we will be getting. So let's put this value, which is basically 1, into this equation. So we will get y of t is equals to minus infinite to see here we are considering for tau less or equal to t, which means you cannot go till infinite, you can only go till the value of t, right? So we will consider minus infinite to t, h of tau will remain as it is, and instead of x of t minus tau, what we are considering value 1, so we will put 1 here and into d tau. So what will be getting, step response, it will be minus infinite to t h of tau into d tau. And again the step response again is integration of my impulse response, right? Because what is it, it is nothing but an impulse, right? So the step response is integration of my impulse response here, and that is the condition for your system to be uh, a system to have a step response. One more thing which I most probably missed, I'm not sure if I have missed it or not, but here when we took multiplication and dynamicity operation, uh, I forgot to mention that the when we took the impulse response at tau is equals to 0, when we multiply any signal, like we were taking this multiplication in this convolution, we were multiplying x of t minus tau with del tau, and we were getting x of t c into x of tau into del tau. So remember, whenever we multiply anything with impulse response, you will get the original value. So we were getting y of t is equals to c into x of t, right? And again h of t is nothing but my impulse response. So that was something that I forgot to mention while we were discussing the dynamicity property, but now it's fine. So we will end this lecture here, and in the next lecture we will be seeing about DT-LTI, discrete time LTI systems. So if you have any doubts regarding this lecture or any other lecture, feel free to mention your doubts in the comment section below. If you have any query, if you have any feedback, if you want to share anything with me, you can also always mention anything in the comment section below. I will try my best to answer your doubts as soon as possible. I will try my best to reply to your comments and give your answer to your feedbacks as soon as possible and as much as possible. So until the next time, thank you very much for listening, and goodbye and take care.